Dear students, in this section, we are going to discuss about the Green's theorem. So in this video lecture, we will talk about the statement of Green's theorem and we will solve different type of questions based on Green's theorem. So let's start the topic Green's theorem. So basically, Green's theorem is applicable in the vector integration. The statement of Green's theorem is as it is. If m and n are the function of x and y and their partial derivative del m upon del y and del n upon del x are continuous in some region R of xy plane which is bounded by the closed curve C, then the single integration that you can see in the left hand side, single integration m dx plus n dy is equals to double integration over this region R del n upon del x minus del m upon del y dx dy. So let's understand the concept of this uh, Green's theorem. Suppose we have a given x and y. So any region which is bounded by the curve, let's say the R is the region which is bounded by the curve C. Let's say it is the curve C. So in that case, if you are integrating, so single integration about this curve C, closed curve C that we say, f dx plus n dy, that is the line integral, it will be equals to the surface integral that we can define R in the form of dx dy. So anyway, you can arrange either LHS or RHS that you can apply. So suppose any function which is not given like constant, if you think of, then you can find the area of the bounded region. Or simple, you can apply the integration using the Green's theorem. So in such case, we can apply the Green's theorem. Now we will see some questions related to Green's theorem. So let's talk about the question 1. Evaluate by Green's theorem the given here integration of minus x square y dx plus xy square dy, where this C is the closed curve and it is what? Cardioids. So first we know about the cardioids, which kind of figure you have, then you can apply the Green's theorem to solve this question. So the figure of cardioids R is equals to a into 1 plus cos theta, that is defined in such a way. So that you know from the curve tracing also the figure of cardioids. So we have to evaluate this integral over this closed path in the polar form that we can say. So once we apply the Green's theorem, so we know the left hand side is the line integral and the right hand side it is the surface integral. So anyone we can apply. R is the bounded region that we have, which is the curve is the cardioids. R is equals to a into 1 plus cos theta. So in the given question, if you go to the question, m is what? Minus x square y and n is xy square. So its partial derivative as defined in the Green's theorem, that is del m upon del y will be minus x square and del n upon del x will be y square. You know x square y square, that is the continuous as well. So we will apply the surface integral so in the polar form. So when we transform the Cartesian to polar, we have the transformation x is equals to r cos theta and y is equals to r sin theta. Applying this, del m upon del y will be what? Minus of x square, so it is r square cos square theta, and del n upon del x will be r square sin square theta. You know, dx dy will be what? R dr d theta, where we know r is the Jacobian in the polar coordinate. So in that case, we will talk about the along the radius vector OA that you can see in the figure OA. R varies from 0 to this curve. So this curve is what it is. R is equals to A1 plus A into 1 plus cos theta. So R will varies from 0 to this one. And in this region, since from 0 to whole circular region that we can angular movement that we can see, so theta will vary from 0 to 2 pi. It makes the one complete circle in angle. So thus in our double integration, I repeat again, R will varies from 0 to A1 plus A into 1 plus cos theta, and theta will varies from 0 to 2 pi. And this we have polar form that we have taken. So now we will substitute all these values in the given integration, that is integration of minus x square y dx plus xy square dy. So it will be what? Del m upon del y that we have written here, and del n upon del x that we have written here. So it is r square sin square theta plus r square cos square theta, and r dr d theta that we can get. So final integration will be here sin square cos square theta is 1, so it is only r cube dr d theta. Integrating over this r first, so it is r4 by 4, and the limit will be 0 to a into 1 plus cos theta. Simple integration that we do here. So ultimately it is what? A 4 by 4 that we have taken outside, which is constant, and it is 1 plus cos theta power 4. So as you know, 1 plus cos theta that can be defined in the form of okay, 2 times if you take here, because 0 to 2 pi that we have taken, so limit will be 0 to pi. To make this, what we do, 1 plus cos theta is what? 2 times of cos square theta by 2. So it is 2 that you can take outside, so it will be a to the power 4 only, and the property that we have applied earlier from 0 to 2a f theta d theta is 2 times of 0 to a f theta d theta, that you can remember. Now we consider theta by 2 is t, so that d theta will be 2 dt, and if theta is varying from 0 to pi, so t will be vary from 0 to pi by 2. So as our integral will be changed accordingly, it will be 8 e to the power 4, because that 2 that we have taken here, 0 to pi by 2 cos 8 power 8 t 2 dt. So 2 to the power 4 that we have taken outside, so 2 cube 8 will be here. Okay, 0 to pi by 2 cos 8 t 2 dt. So ultimately it is going to be 16 e to the power 4, and from the integration that you know, it is what? It is a beta 9 by 2 into 1 by 2. So that formulation you must remember here. So beta 9 by 2 is what? Gamma 9 by 2, gamma 1 by 2 upon gamma 9 by 2 plus 1 by 2. So it is 5. Gamma 1 by 2 is pi. So, and gamma 9 by 2 is what? 7 by 2 into 5 by 2 into 3 by 2 into 1 by 2 into gamma 1 by 2. So gamma 1 by 2 is what? Square root of pi. So it is overall total that we get here 35 pi by 16 e to the power 4. That is your answer. So I hope so this make you clear about the use of integration with the help of Green's theorem. Now we talk about the second question. Here we have to evaluate this line integral is given by the Green's theorem, where C is the boundary region by uh, y is equals to 0. So y is equals to 0, that x-axis, y is equals to 2x, that is we have drawn here, and x plus y is equals to 3, this one. So this area is the boundary region that we can see here. So over this area we have to integrate. So this is the question. So m is what? X square plus 2y, and n is 4x plus y square. So now we can write the Green's theorem, that is integration m dx plus n dy is what? Double integration del n upon del x minus del m upon del y dx dy. So in that case, R is the here R is the boundary region by the given that we can see in the figure also. So m is x square plus 2y, n is 4x plus y square. So del m upon del y is 2 and del n upon del x is 4. So 4 minus 2, it will be 2 only. So by substituting this, it will be 2 times of dx dy. So that is 2 times area of that triangle OAB. So base into height into that we can define. So as you can see in the figure, it was defined. So it is total 6 that you get as the answer. So very quick, we have seen the second example. Now we can see the third example. As I said earlier, we can find the area with the help of this theorem also. So find the area of the region bounded by the parabola y is equals to x square and the line y is equals to x plus 2 or y minus x is equals to 2. Anything that you can make it here. So ultimately y is equals to x plus 2 and y is equals to x square is the parabola. So what we can see, the figure that we cover here, it will looks like that. So y is equals to x plus 2 that we can define. Actually, this line will go a little bit more so that it will be here. It is minus 1, minus 1. If we put here x is equals to minus 1, then y will be 1. So it will be plus 1. And this point of intersection that we can define here. So I correct it here. So what we required here, we have to find the area of this region. It is given. So either we can move in single integration or we can move into the double integration. So what? So we have to integrate over this area. So I will make this point here. So this area we have to, over this area we have to find. So either we can move through the, as told earlier, by the line integral or the surface integral. So what we can see in the given question, the point of intersection, that is y is equals to x square and y is equals to x plus 2, that can be obtained here is 2, 4 and minus 1, 1. So we can solve it. Y is equals to x plus 2. So x plus 2 is equals to x square. So this quadratic equation that you will get. And by solving this, you will get x is equals to minus 1 and 2. And y will be respectively, by putting the value of x in any equation, it will be 4 and 1. So we have this 2 point which is bounded by this region, which bound this region with the help of these two curves. So A and B are the that two point here that we have considered, and we have the two paths. That is, the first one is AOB, that is the curve, and second one is the what? BA, it is the straight line. So in the given question, that area will be 1 by 2 integration of x dy minus y dx, that we can define here. So this integral will be with the help of two this curve, that is AOB and the BA. These two paths we will take to complete this area. In that case, first we use the AOB, that is the path is parabola y is equals to x square. So dy will be 2x. So x varies from -1 to 2 that we can take here, from -1 to 2. So over this area we integrate. So what we get here, x dy minus y dx. So it is -1 to x into 2x. Dy is what? 2x here, and minus of y is equals to x square. So that we have considered. So ultimately it is 2x square minus x square. So it is x square dx only. So integration of that I put right here. It is -1 to 2 x square dx only. So integration of this is which is quite simple, x cubed by 3 and limit is -1 to 2. So by applying this, what we get, it is 8 by 3 plus 1 by 3. So it is 3. 9 by 3, it is 3 that we get. So this is the first part that we have integral. Now we choose the path, that the second integral, that is what, this one. So over this, what we see, it is the equation of a straight line, that is y is equals to x plus 2. So dy will be dx, and x again it will varies from 2 to -1. So this way we are talking about. So in this case, integration of x dy minus dx will be integration from 2 to -1, and x dx will remain same, y will be x plus 2 dx. So x minus x is 0, only the 2 minus 2 is there. So integration is x, limit is 2 to -1. So ultimately you get here 6. The required area will be 1 by 2, 3 plus 6. So ultimately it is 9 by 2 is your answer. Now come to the last question of this section, that is find the area of the loop of the volume of this curve, that is x cube plus y cube is equals to 3axy. So this is very important part. So to solve this such kind of problem, we apply the what, the polar form. So x is equals to r cos theta and y is equals to r sin theta, that we take the transform. And the equation of curve is given, x cube plus y cube is equals to 3axy. So by putting these values of x and y in the polar form, what we get, r cube cos cube theta plus sin cube theta is equals to 3a and r square sin theta cos theta. So r will be what, 3a sin theta cos theta upon sin cube theta plus cos cube theta plus sin cube theta. Now we apply the Green's theorem over the boundary region, which is by the closed curve C in the polar form. So by using the formula of area that we get here, 1 by 2 integration of r square d theta. Your graph was like that. And this kind of. So the closed path that we have, the angle will be 0 to pi by 2, it is moving. So the limit for this loop will be what, 0 to pi by 2. And it a will be 1 by 2, 0 to pi by 2, that is r square, 9a square sin square theta cos square theta upon cos cube theta plus sin cube theta square. So we can make it by taking the cos theta common here. So it is 1 plus sin cube theta by cos cube theta. So it is going to be 1 plus tan cube theta, and cos to the power 6 theta that you can take outside. So ultimately it is what, sin square theta and cos square theta, that tan square theta, 2 power will be cancelled and remaining 2 cos square theta will be here, it is sec square theta. And 9a square that we have taken outside. Now we put here 1 plus tan cube theta is equals to t. So 3 tan square theta sec square theta d theta will be dt. So that we have taken here the numerator part. Now as theta will be 0, so t will be 1. Theta will be pi by 2, so t will be infinity. So area A will be what, 9a square by 2 integration from 0 to infinity dt upon 3t. square. So in that case, the simple integration that required, so it is minus 1 upon t, 3a square by 2. So by putting the limit, once you put the limit infinity, it will be 0, and it is what? Minus minus plus 1. So ultimately, your area will be 3a square in the polar form. So we have used the Green's theorem to solve a number of questions. I hope so. It make you clear about the use and application of Green's theorem. So thank you for watching this video. So if you really enjoyed, so you can like this video, you can share it with your friends. And if you are new, then definitely subscribe our channel for the upcoming video lectures. In next, we will talk about the Gauss divergence theorem and the Stokes theorem and questions related to these theorems. Thank you for watching this video.